Good morning, and thank you, Joao, for inviting me here to help in this workshop that is very interesting because of the contents. And thank you for coming here, those of you who are especially coming from far away, like I sort of came. And I'm going to give you an overview about geometrical energy methods that are defined quantitative variables. I'm responsible for the development of the quantitative variables module in MD, which does many, but not all, but most of the methods that we're going to discuss in this workshop. And of course, it's a library, software library, so it's very flexible in a sense. So a lot of people develop methodologies that were completely new and that you didn't even know about. But I'm going to try to do my best to point you to every resource so that you get the best overview of every possible technique. I'm going to, is the volume good, fair to look?
Cuts out at
Cuts out? Should I can speak a little louder, but yeah, even if it cuts out at times because I'm quiet. Okay. I'll try. I have good news and bad news. The good news is that this morning of lectures will directly tie on what Chris Schiffer talked about on Monday, and what also he's going to talk about tomorrow. And so it's going to be both a refresher, but also at the same time another take on it from a different person, who of course has interacted with them a lot, so we are aware of what we're presenting here. So hopefully, because the theoretical foundations of most of these methods are common, once you get to understand one of them, you also understand the others much better. The bad news is that my slides are not as nice looking as Chris's. This is safely, arguably the prettiest slide in the set. I asked actually for help to my friend Fabrizio, who is one of my collaborators at NIH. I kind of hop between two campuses nowadays, mostly because I do different projects there, and I don't get to do many free energy calculations in the projects in the Thermal Materials Institute. But of course, every part of it is interesting in its own. And before I start, I wanted to let you know that I really appreciate being stopped for a question. I don't have like a set time. I allotted enough slides to cover the material, but of course it's not going to go too much in depth. So if you have a detail that you feel is missing, please feel free to ask it now before I move on, etc. I will have some time at the end in the second part of the second section where I'm also going to try to run some of the demos, the simpler demos that I provide with the code. And then also this afternoon you're going to dive in deeper into one of the specialized tutorials that deal with one particular subject. And I'm here to try to help you with any one of them. So by all means, as I move through, don't feel wrong, don't feel bad about interrupting the pace, because this is precisely what I was looking for questions from you. So to start, are there any questions before I move on? Let me give you one slide at least before. So you may have seen a similar slide from Chris a couple of days ago. And it's basically a summary of the different methods that you use to measure free energies. Thermodynamics, statistical mechanics give us laws that relate physical properties to one another, and basically all of them to the partition function of the free energy. And in a simulation, you know everything. I mean, you may not know everything about the system you're studying when you're simulating it. Certainly when you get your paper reviewed, some people will argue that you don't know what you're studying. But definitely within a simulation, you're in the best position to know everything, because all the atoms have coordinates, velocities, charge if you're using a model that goes beyond the charm force field. Everything is available to you. So you should be able to access any one of these properties and use them to measure free energy differences, which is what this workshop is about. Historically, the first method is thermodynamic integration. It was introduced by John Kirkwood in the 30s, and was later extended by his after he was studying with him, but in the 50s, by Robert Tronsick, who actually was a professor and then a staff and career scientist at NIH. Fiorin's perturbation is basically an extension to a finite step of the continuous integration of Ti. And then there's a big umbrella, of course, that covers most of the methods that are based on probability distributions. Of course, statistical mechanics is based on probability distributions. So, although maybe this may be too general, but having more than 4 categories seems like that. And also, you have a lot of subcategories in here. So I'm listing here umbrella sampling, then multi-state, the Bennett acceptance ratio, and the multi-state extension to that the Pandy group uses, metadynamics. All these methods are encountered to measure a histogram of probability distribution, and that we use to be extracting energy. And another way that is theoretically different, quite different, is the one introduced by Jarzynski, which you've seen in combination with Steele and Lee experiments, both real and simulated. I guess the real experiments are not called Steele molecular dynamics, but they're still steering and there's still molecular dynamics going on. So I think we can put them in the same category. And this is quite different because contrary to all the methods before, it does not rely on you trying to go towards the thermodynamic limit. It does not assume the simulation is infinitely long. It assumes that you have like an infinite number of very short and very graphic simulations. And we will get to that in a little bit. The first one is thermodynamic integration. And it is the most straightforward approach you can take. Suppose you don't know anything about the literature from these past 80 years, but you want to calculate the free energy. You know that the free energy is a function of many variables, and these variables correspond to the positions of all the momenta of the atoms involved. You have a path in this very high dimensional space, and this is the path that theoretically we will follow the lowest free energy. And while it is an assumption to do it for your simulation, it will always be true in a real system as you know. So imagine this path that brings you from the state 0 to the state 1, if you want, from the state A to the state B. And you can just integrate the free energy as a function of the parameter that gives you the displacement around this path. We call it lambda here. It could be the lambda of chemical transformations, and Brian talked about it yesterday. I'm not going to talk about that kind of lambda. I'm going to talk about a lambda that is defined based on a function of atomic coordinates, but the statistical mechanical formalism doesn't distinguish that. You should be able to connect the two states with an arbitrary path, for as long as it is continuous. And the problem is, of course, that it's an integration, all right, but if we don't know the derivative of the free energy around this path, how can we calculate this integral? And this can be done by reworking the terms a bit. So those of you who have taken statistical mechanics courses are probably familiar with the quantities shown here. For the others, I'm going to briefly say here that what you're doing is taking an integration of the derivative of the free energy. What you're doing then, you're expanding the free energy into the sum of states that statistical mechanics defines. So you have the partition function, the sum of the states, and then the exponentials, the Poisson exponentials. Now, you're going to switch the order of the two operations, the derivation and the sum. They can commute. So you can sum outside the derivative, which is what you're doing here, and then you can derive the different energy levels because you're summing over them. So what you end up doing is you're summing over the energy states of the system, whether these are discrete energy states like in a bound molecule in terms of orbitals, or continuous energy states like you have in molecular mechanics, same thing. The point here is that once you have transformed this into a sum, and there's a weight here, there's normalization, so this is actually an average. You're taking basically an ensemble average of the derivative of the energy with respect to the order parameter lambda. The brackets here indicate an average, And they indicate an average in the equilibrium ensemble. This is important because the Jasinski method does not rely on that. So this should be a separate index. It's very quickly how we talking.
Yeah, that microphone has a few issues.
Yeah. Okay. So to summarize, we have actually found by working out these terms that the derivative of free energy can be expressed into the average of the forces once these forces are projected on the order parameter. Of course, again, we're not fully solved the problem. Well, we made it much more manageable because we may not know from the beginning the free energy, but we can do a simulation, do this correction of states, and definitely know the energy function. And now it's a matter of calculus, not a matter of running a simulation. So the method, which we now call thermodynamic integration, again was derived by Kirchhoff, and it's basically this element here. And it calls this number, the derivative of the internal energy, I call it here U, or E, is the energy function, the total energy that Nandi, for example, will bring on the alpha. So the derivative of that number with respect to the parameter is the number that you're going to take the average of. And once you're taking the average, you can integrate it numerically. And it's a numerical integration, so it's a stepwise sum. Most of the time it's going to be performed by a code, for example, your chemical code, or some of the coding corrective variables, but you can do this sum yourself. It's a simple target sum. Of course, how do we set up the simulations to sample these points? If it's a discrete numerical integral, each point should be a separate simulation. So each point where we're taking the average with the brackets should be a simulation that is properly initialized and is run for long enough to collect a good average that is numerically stable. There are, of course, different approaches to do that. One is the classic one, which is the constrained approach, and that was done for chemical reactions. You may have read a paper from a few years back about the blue moon ensemble, which is basically a constrained molecular dynamics inference calculation using TI for, like, for example, the distance between two atoms and the bond breaking between them with a particle molecular dynamics. So you run many simulations and you run them with a relatively fine grid. Here I'm assuming 100 points. You may be able to afford fewer points between 0 and 1 or between the initial state and the final state. That will depend, of course, on the system. Every one of them, you just run a simulation and you tell the code to fix the number parameter, hard fix, a real constraint, not an MD constraint, a constraint that actually prints always the same number for lambda. And then you have to tell NAMD, of course, depending on what code you're using, it will be different syntax, to basically apply constraint forces just like the shake forces that are used to fix the lambda parameter in place. And then these constraint forces, of course, will be met by another force that the system projects onto this lambda parameter. So that's the force that you're collecting, that's the du of the lambda that you're numerically sampling and then integrating. Of course, you don't have to do this necessarily by keeping lambda fixed. Actually, for more complicated order parameters than a distance, where you don't necessarily have a nice algorithm like shake, it may be more difficult to fix, to make a hard constraint for the lambda parameter. So it may be easier, and it's actually also quite powerful anyway, to run a simulation where lambda can change. Maybe it's an unbiased simulation, so lambda maybe will go spontaneously from 0 to 1. So you actually are able to see the entire spectrum of states. Or most of the time, you will put a bias, which is what we're going to talk about in a minute. But basically, you're locating a grid ahead of time during the simulation, and for each lambda point, you're going to accumulate a different average. And once you have collected enough statistics on this grid, then you're going to integrate it at the end of the simulation. So the two approaches are exactly the same in the way that you measure the free energy, but they're not the same in the way that you set up the simulation and the way you enhance sampling. So I guess this is the first example of one thing that really, one of the very few take-home messages that I would like to give you is that free energy, there's like, except the title I think is very useful here because it distinguishes the enhanced sampling part from the free energy calculation part. You can have one method for the sampling, one method for the free energy measurement. For one method for the enhancement of sampling. Sampling, of course, is always required for the free energy calculation. But the two methods may not be the same. They may be closely related, like in ADF, which uses thermodynamic integration. And this, I'm sure that Chris has told you about on Monday. And if not, we're going to talk about it there. And but you can actually mix and match. For example, many people in the charm community use an umbrella potential as a bias for enhanced sampling and the thermodynamic integration behind to measure the free energy. Now, of course, it comes down to what reaction coordinate should I use. What is the lambda parameter that will give me the best results? There is no general rule to this. It's really specific to the system. And of course, there's guidelines that you should be aware of. Read the literature as much as you can, because there's a lot of information there. But you probably, of course, will always find the success stories where like the reaction coordinate was good, or actually appeared to be good, and not the ones where it didn't work. Of course, talk to your colleagues if you have done some work before about this. But we presume here that there's going to be some work done by you studying your system and studying the literature about it or similar systems to pick the best lambda that will give you the free energy calculation that you need. One case where lambda is easy to choose is when you have, for example, a chemical transformation. It's very natural. You have a switching between an A model and a B model. You may have different lambdas if you're switching different parts of the Hamiltonian differently. This you probably talked about yesterday. But let's assume for simplicity there is one, and that's the one that you can use to do free energy calculation. I'm not going to talk again about that because I'm talking about geometrical free energy transformations. One example here from one of the original lecturers of this workshop who couldn't make it here, that's Benoit, who all of us know. And this is one of the famous papers from his group, where he did a free energy calculation of the ion conduction to the KCSA channel. So each one of these is a different umbrella sampling simulation. And here, the reaction coordinate was the most natural one. The position of the ion along the membrane normal. So I rotated the membrane here so you can see the x-axis. And but basically, this was one example of a simple to choose a reaction coordinate. Of course, there's a more sophisticated and better converging studies also for ion channel conduction. There's other cases where it's not so difficult, and people actually do interesting work, but to my knowledge, there isn't really the reaction coordinate for protein folding, a number that you can actually do thermodynamic integration on. This was done here by Fedorino and the Schulten group, and this was done with a brute force simulation. And if you have to sample all these states using a single geometric parameter, you could do that, but I gave you write that parameter as a 1D path. Most of the time, you will just have to use a path in higher dimensions. And this will be talked about tomorrow by Chris. So back to the case where we have chosen lambda and we know it's good, which is hopefully the case for everybody, but of course, this is what we aim for anyway. In the case where lambda is a good reaction coordinate, let's work out a little more what these forces are including. And I would ask maybe if this is a good time for us to ask a question. I haven't had one yet. Yeah.
Can you talk about maybe the differences between constrained and unconstrained sampling and why would you like to use one over the other? Or is that a bit more large of a subject then?
No, I mean, it's a larger subject because it's general.
Okay.
But, I mean, I can say briefly that it really, the effectiveness of it depends on what you're going to use to enhance the sampling. If you use the constraint approach, you're enhancing the sampling by basically setting the system at every random point. And there, basically, if there is a barrier, well, you're going to set the system there anyway. So that's how you enhance the sampling, by enforcing the constraint. If you relax this constraint when you use the umbrella sampling, you're putting a potential which will act on lambda, will keep it in the neighborhood of the point that you want, and then you're going to sample it there. So if you're doing that, you could be tempted to say, well, I measure the derivative of lambda at the center of the umbrella, which could work if you have a very thin umbrellas, but in practice, umbrellas need to overlap, so they need to be, they have to have finite width. So lambda will be different in the interval that each umbrella spans. So that's when you actually should be using the unconstrained thermodynamic integration, where basically you put an umbrella potential, and the umbrella potential is the well-defined center, but on each point in the parabola, you're going to measure a different value for this. So, and then you, for this grid, you make it as fine as possible, of course, given the amount of time that you can simulate. But basically, yeah, you should be, and every time you're applying forces to lambda and you're letting it evolve over time, right, you're in an unconstrained approach. So I would say the best situation is that in unconstrained is just say, this is my interval. I choose how many points I'm going to do the numerical integral on, and whatever potentially apply to that, umbrella sampling, thermodynamics, Stirred D, nothing at all. You always use this numerical grid. So in a sense, unconstrained thermodynamic integration is the measurement part is just like the constrained one. It only matters what's the time series of lambda. But how to do the measurements is exactly the same.
Sorry, it's probably kind of basic, but in practice, when you're measuring this delta U, delta lambda, what are you physically using? Using the potential energy function in the log file?
No. Well,
No.
You could do that in some cases, but it's not. It's kind of dirty, as you probably know, and also not very efficient because then you're limited to either you have to print output at every step,
right,
which will not make your simulation run very fast, or you have to, you have to reduce your sampling. The ideal case is just in the code, accumulate at every step. And this question is not basic at all. It's very important how do you practically do this. How this is done is that an MD engine like NAMD has, of course, the information about the total forces because they're used to integrate the positions. They give us the acceleration of the atoms. These total forces are, in this case of thermodynamic integration, are not only used for that, are not just used by integrator, but are also communicated to another piece of code. In the case of NAMD, this could be Corvus, for example. And this other code, basically, or yeah, the chemical FEP module, well, which defines its own lambda, but basically, you are sharing this information of the total forces to another code. And then the code will actually project, and I'm going to talk about the projection in the next few slides, but basically, you're using the forces that the entire system through the force field projects on the lambda parameter. So you're using forces on the individual atoms. You're using 3 vectors, x, y, z, x, y, z, x, y, z. And these are the numbers that actually you're using. And then mathematically, you take these many x, y, z vectors, the forces acting on the atoms, and you reduce them to the one dimensional space where lambda stays. And the mathematics of it can be relatively simple for a distance variable. For angles, the heaters is more complicated. For RMSDs, it's a bit more complicated. And for some variables, this is actually not done at all because it's too difficult mathematically. But basically, thermodynamic integration uses the forces that act on the atoms. So what you're measuring here is the free energy to thermal integration, but what you actually measure microscopically is the force that acts on the atoms that you picked. So the way we do this, we can do, because this, of course, derivative may be simple to express for the alchemical FEP, because then the energy function has lambda right in the formula, so you can just derive it. Easy. Most of the time, you will basically have an energy function which is a function of the Cartesian coordinates. So this is an x vector that is the x y z, x y z, to z, to all the atoms in the system. So this is a 3n dimensional vector. So you do the gradient in 3n dimensions of the energy, so you get basically the forces at that position. So again, this is what you're measuring. And you of course have it because you're running a simulation, so you must have the forces. And then you derive, of course, with respect to the position, because that's the forces, and then you derive the positions with respect to lambda. And then you basically, this is the product, so there's a sum over all the dimensions. Now, there's one thing that is interesting, well, two things that are not real at all about this derivative here. Here you're deriving a 3n vector by one parameter. And most of the time you have lambda as a function. Most of the time, just when I'm talking about Jacobian, things go. Most of the time, the lambda is a function of the coordinates, and you will have the derivative of lambda with respect to the coordinates. The other one, not that easy. But you can have techniques to derive that. One thing that is important to know is that only the derivatives that are orthogonal, that are parallel to the gradients, so only the derivatives of the Cartesian coordinates with respect to the other parameter that have a component along the force will matter. The other ones will not appear in the dot product. So if you know geometrically how your variable is defined, if you know, for example, that you're measuring the energy on the z coordinate, x and y are orthogonal to it, will not appear in this dot product, so you don't actually need to do this for x and y. The other thing which is more important is that you're doing an integration here, so you're doing a change of coordinate. And basically, you need to calculate this function, but also you need to remember that a change of coordinate in multiple dimensions could actually give you a changing intensity of states. This is where the Jacobian comes about in some more dimension now. So the integral that you have here, this is how you do integrate over lambda. This is the lambda integration. And here you can actually integrate over all the coordinates that are within that lambda manifold, within the slice of the space, within the last of the space that are constant lambda. And this can be tricky. What you can do is instead of taking always the integral here on the manifold, which may be difficult to get, you can actually change the coordinate to the three-dimensional vector of the 3n dimensional vector of Cartesian coordinates to one system where you have lambda as the first pointer, and then some other coordinates which you call q with, you can call whatever because those are the ones that you don't care about. What happens is that you get this derivative here, which is good if you have a simple function of the simple function, where the energy is a simple function of lambda. For example, if you have a distance, then of course you know that the forces acting on the distance, you already calculated them because you already calculated the Reynolds-Jones equivalent force of the distance between two atoms. But then you have this term here, which is going to be important because you need to know distance. Like to do streams, right? Okay. So the second term was basically defined as a term coming from the change of coordinates. And the mathematics is not trivial, but in the end it gives us results that are pretty well established. So you can look into the paper by Emily Carter back in '89, where they actually derived this formula, which is used by most thermodynamic integration definitions, or simply use it knowing that it's valid in every condition of equilibrium, and actually, in this case, is even a condition of just having a geometrical transformation between the three Cartesian coordinates and the lambda coordinate. So what is this term here? What does it represent physically? If we talk about it in these general terms, it's a little vague. In the practical example, that's one of the distance between two atoms. Suppose we're doing the free energy calculation as a function of the separation between sodium and chloride, in this case, or two molecules, even two proteins. In this, what you're doing, basically, you're deriving the energy with respect to the radial distance. Let's call it rho here because I'm going to use power to get the long behavior of the free energy. So you're deriving the energy with respect to this distance. And again, if you have sodium and chloride, you're going to calculate the van der Waals interaction and the Coulomb interaction between them. So the derivative of the energy with respect to the distance between the two of them, you know it. What you need to do basically is just add the terms corresponding to the forces on the count from the rest of the environment to our molecules. But again, this is easily done because the mathematics of deriving the energy with respect to distance is already there. The thing that you don't have is the derivative of the Jacobian, which you may have to do for a new variable. But the nice thing is that it doesn't contain any term about the energy here. This term is purely geometrical in origin. It does not depend on the particular system. It does not depend on the force field you're using. It only depends on the reaction coordinate that you're picking. So if you're picking a distance variable, no matter if it's the distance between sodium and chloride or between one protein and its receptor, it doesn't matter. You're always going to have a Jacobian term which is always the same. And if you're working in polar coordinates, you can show that it's basically, once you take the derivative of the respect to the radial distance, is this term. And if you put this into the formula of thermodynamic integration, you get that the free energy has a contribution here, which is 2 kT logarithm of the distance. This is the Jacobian term for a potential mean force between two atoms, and it's always going to be there because it depends only on the distance. So it's going to be the Jacobian correction for two atoms, or like two molecules, or two very large macromolecules. And depending how much is the distance, it can be relevant. The logarithm here is a slow function. But if you go to a very large distance, this will kick in and will be part of your potential force. Now, of course, you don't have to know it necessarily to sample it. Other methods than thermodynamic integration, they are measuring indirectly without knowing what it is. Thermodynamic integration has a special requirement. It needs to use the forces acting on the atoms, Cartesian coordinates, and does the projection on the reduced space of collective variable. So this projection comes with some nonlinearity, and the nonlinearity is what this term is about. And now there's a problem. Because we have defined a potential mean force from statistical thermodynamics as the logarithm of the radial distribution function, the G of R. And we know that the G of R is tends to 1 for large distances, and tends to 1. And so the free energy with respect, as a logarithm of we should tend to 0. So if you take the logarithm of the G of R for large distances, you should have a 0 free energy. But this will not give you zero free energy. It will give you a free energy that keeps going down, slowly, but it keeps going down. So what happened here? This is an issue of how we have defined, in this case, the potential energy force. We define the potential energy force between two species. So if you have sodium chloride, you have many sodium ions, many chloride ions in the same solution. So for every pair, there's always going to be one sodium ion within a certain distance of the chloride ions, and so of course more, but like for the pair, there's always. But then they cannot be the same atoms. Now, what we did here was we did a calculation for two specific atoms. But if you put like one atom of sodium, one atom of chloride in a macroscopic box, most of the time they're not going to stay nearby. Most of the time they're going to be away from each other because the states are very many, the macroscopic box is big, and the atoms are very small. The reason why we have defined a GeoVar like this is because in a macroscopic solution, you have many of these atoms or molecules, so you can just swap them, basically always have a sodium chloride pair within distance. So basically, once you integrate over the whole volume, then you get the GeoVar tends to 1. But remember, when you're doing a free energy calculation, you're doing it for two molecules. And the system may be periodic, but you're making it big enough that the periodic images shouldn't see each other. So for all effects and purposes, you're simulating one sodium and one chloride in a very large box. If you try to calculate the free energy with any free energy method, including free energy integration, the free energy will keep going down because there's a large entropy term that arises from the fact that there's many states at large distances. The difference between thermodynamic integration and all the other methods is that thermodynamic integration requires this term explicitly. So you can use it or not use it. You can use the convention that gives you the definition of the free energy as a function of the GeoVar, or you can use just the plain definition integral of the derivative integral of the thermodynamic force. You're seeing in ABF, which is basically a thermodynamic integration with an inductive bias, the option hides Jacobian. If you've used it before, you've seen it. If not, you will soon. This is what that flag does. For potential reinforced is always the same. You can just add or subtract this term, which is very easy to calculate. It's a formula that can be pre-computed by the beginning of the simulation, and even by you can plot the pure potential mean force with this term, so the free energy goes down, or this term subtracted, and in that case the free energy should go to 0 for large distances. And it's your choice how to plot. But the nice thing is that for a distance variable, you know what this term represents. The second thing, which is not related to the distance, where we have a convention here, is that the distance is not the only variable that has a non-constant Jacobian. It has a non-zero Jacobian term. The root mean square deviation is another variable where the formula is not so simple, but if you go to the appendix or paper or the manual for the corrective variables module, and also, of course, the literature of people who have worked on these problems, there is a non-constant term for the RMSD as well. It will not depend on simple numbers. It also depends on the reference coordinates that you pick for the RMSD. But again, it depends only on that. It doesn't depend on the force field you're using or on how long you simulate. So what this term will affect is how quickly you can converge it to the entire PMF. Because there is a logarithm like this for the distances, it's just a logarithm of more than just r, but there is a logarithm of the RMSD. RMSD equals 0 will diverge. The free energy of RMSD equals 0, it's infinitely positive. So if you're doing free energy calculations with an RMSD variable, you're perfectly fine doing it, but remember that there is an infinitely low entropy for the RMSD equals 0 state. The proton that you're doing the RMSD on will very rarely come back to the initial state reference state. The RMSD equals 0, is an infinitely small piece of the phase space. And the free energy for that will be project accordingly. So if you see a huge spike as RMSD equals 0, it's perfectly normal. This is the Jacobian going on. Now, the question is, if you're doing ABF or thermodynamic integration, you have the option of taking the Jacobian on or off because it's pre-computed. If you're doing, of course, if you have a formula, you can also do it in the plots. If you get the PMF from Urbana sampling, you can decide where to put the Jacobian in there or not. Same for dynamics, same for steering the engines. All other methods are thermodynamically rigorous, but thermodynamic integration is the only one that gives you explicit treatment of this term. It requires it for its own calculation, so then you get the option of choosing what to do with it. Knowing that some variables have a Jacobian that can be changing a lot can actually be important in Python simulation. Nice time for another question or two. Yeah.
How large is the term state of R usually? So how large is it?
Well, so yeah, say that R.
What's the distance unit?
So it is whatever you want because in the logarithm, if you can divide by angstrom, divide by nanometers, but it's going to be a constant that you take out of the logarithm. So basically, it's going to be an additive constant to the free energy, and it doesn't matter for free energy differences. But so yeah, let's say that we're measuring R in angstrom, I'm using units that NAMD does. So then this logarithm of R, for example, you can calculate easily that if you're sampling up to R equal 10 angstroms, then you are going to have 2 kT, so more or less 1.2 kcal per mole, times the logarithm of 10. So it's not a big term, but if you go far enough, the logarithm eventually will kick in. Yeah.
So if it comes close enough, does the user have to provide the threshold, or is it already inbuilt into the?
I would say that if you're doing the separation of two atoms or two molecules, you don't go to zero distance because you have van der Waals repulsion. So generally, you don't have to do anything for that. Those are states that are not sampled anyway. But the reason why I brought up about the RMSD is that I could actually dig up the formula later, but it has a similar problem, but RMSD 0 is allowed. So you say, this is a state that is physically accessible, but it's like one state, one point into a very high dimensional space. The entropy of that point is very high. So basically the free energy the entropy of the point is very low, so the free energy will be very high if you go to RMSD equals 0. As soon as you're like within the range of thermal motion, 1 or 2 angstroms for a stable floating structure, then you're already not, and it's already not a big deal. Because then RMSD equal 1, okay, say that we use angstroms, but of course if you use another unit, it just comes as an additive constant. So that point, yeah. Where it doesn't change so much for the range of RMSDs that actually the simulation will sample. But because you may think, well, RMSD 0 should be allowed, why can't I go there? The reason why is that it is infinitely hard to go there for entropic reasons. So don't feel bad if you see a spike at RMSD equals 0. RMSD variable as for potential reinforced calculations, you should take it from the thermal motions, a stable structure, 1 or 2 angstrom, whatever is the minimum value that will give you to all the values. But low values are of the RMSD, they don't make much sense. Okay, well now I can move to the next, which is free energy perturbation, which I'm going to mention only very briefly because the theoretical foundation is the same. Like I said, Swansea was a Kirkwood student and he worked out FEP there. And also, for geometrical transformations, it's not so convenient to do FEP most of the time in the thermodynamic integration because you have continuous transformations. You do a constraint thermodynamic integration, you don't need to do finite steps. But for chemical FEPs or other cases where you may want to continuously switch the potential, you can do it in stages. So the formula, which can be derived, although I've done one derivation sort of on a slide, that's not the one for every method, let's focus on what's different between them. The difference here is that whereas in thermodynamic integration we were measuring the forces, now in FEP we measure finite energy differences. So we're not taking derivatives here, we're taking delta energies between the two states of the system or between two Hamiltonians. So the equation here by Swansea is the one that is used in pretty much any FEP methods. Basically, it does the derivation of course, in the assumption that you have a very smooth function and also that you sample infinitely long. So that this bracket here is the ensemble average and the equilibrium ensemble. So basically your simulation is so long that it covers completely the canonical ensemble. This is the definition, of course. In practice, you're going to have to collect states. So basically, you're going to run a simulation where you have one system, but it has two energy functions, UA and UB. And you keep recording the energy difference between the two. Of course, you're going to have to use one of them for the forces. I mean, you can of course evolve the system using a mixed potential, but there has to be one potential, not two. Only one potential is responsible for the equations of motion. By convention, you use the A, the first one, and then you do the exponentials this way. So you have the exponential of minus UB minus UA, the delta. And of course, A can be the state for lambda equals 0, or you can do many windows, like 10 or 20, and then A basically can be the lowest one, and then B is the one up. So each A or B may not be lambda equals 0 or lambda equals 1. It can be both mixtures of A and B. So you have windows that go this way. And the formula works. It works quite well. It doesn't add anything more than thermodynamic integration. It is just a finite step extension of it. Now, why is it useful in mechanical transformations? Because it's very difficult to evolve continuously the system, to evolve continuously with lambda. I mean, you can do lambda dynamics, but traditionally it is easier to think about doing simulations at each interval separately. I think that, well, every time you change the energy function, you're going to move the system a little out of equilibrium. So you just run one window with a choice of lambda, you're going to discard the first few steps and then accumulate from then onwards. Yeah.
So when you were talking about that unconstrained approach in thermodynamic integration, is that the same as lambda dynamics? Or?
If you use thermodynamic integration to measure free energy, yes. Thermodynamics is a simulation protocol, but the free energy calculation, well, it's going to be one of those methods, and thermodynamic integration, yes, can be one.
So is thermodynamic integration considered to be a slower growth method or just field perturbation?
I would say, well, it depends on the number of steps using in each. Definitely, thermodynamic integration is assumed to be continuous. Yeah. So in practice, you're always going to do like a numerical integral, but you're going to pretend you're doing a continuous integral, an analytical one. In FEP, you explicitly say you're not doing an integration, you're doing finite steps. That's the difference in the way that the formula itself is defined. So instead of doing this calculation, you see the delta F here is the direct integration of the thermodynamic force. If you do two finite steps, this is like the first order approximation, if you want, the first order term, and of course, because you're doing like an integration, the the first order term is the one that is most important. But if you're doing finite steps, higher order terms are important, and they're all included in the exponential. So the difference really is whether you're doing an integral or a finite sum. And that's what we're doing to TI and FF. Joao, the time there is accurate or I don't know?
Yeah, so it's 9:54.
Okay. So I mentioned the chemical FEP. I don't think I need to spend too much more. Definitely, I'm not the best person to ask about it anyway. One thing that is important is to know that the method is rigorously defined, and this formula will work if the windows are too far apart. While your simulation, your statistical coverage may be crappy, but this formula, precisely because it's a finite step, will work anyway. And now I move on to what is actually more relevant for geometrical field equations, which is using probability-based methods. Yeah, so we talked a little bit about FEP, but really, the message I want to convey is that FEP is very practical, but it's mostly used in the chemical transformations. So if you're doing PMFs, mostly you're going to do thermodynamic integration, probability, or sometimes Jacobian, but you'll see whether it's worth it or not. So now, for probability-based methods, basically, you're not anymore using the forces or the energies. So it's actually very low demand for the MD engine because it can be all done in the analysis phase. For example, take one of the best examples is the MVAR method that the Panda group uses in the ensembles or simulations done by Fiorin Home. Each of those simulations is unbiased. It's a straight molecular dynamics. Everything is done in the Markov state model analysis. So you can always compute the probability distributions for any parameter that you want in the post-processing phase. And this is the reason why there's many probability-based methods, because you can always compute a histogram of pretty much anything, and you can always get a free energy from it, provided, of course, the derivation is theoretical. So I'm going to start with umbrella sampling, that's the classic one, and measurement dynamics. Again, I'm focusing here on most of methods that we use in NAMD as much. Of course, nothing prevents you from using MVAR. It's just that at that point, you're not really using much features from MD. You're using a post-processing tool. But definitely, you should think of these methods are all sharing a common foundation and try them all if possible to see what it gives you the results that are best for you. The thing about the partition function and the canonical ensemble is that you can always compute the probability distribution of a variable v like this. So you can take a state, So if you have a microstate which you can label because you can always define a region in the Cartesian space, or at least with system you can always count it. You can get the Gaussian integration. This is probability. And of course you have, I don't even need to explain it too much. This is formulas that you've seen already. You can always take the ratio between the two partition functions, and then basically you get, this will give you the exponential between the difference. And basically it boils down to just, in practice, taking the explicit calculation of the partition function. So the explicit sum over states or exponential states, and basically you have here, say that you're calculating the probability distribution of the state of the macro state one. All the states, all the microstate V that have lambda equal 1, you extract them from the sum, and this is what the sum shows you. And of course, if you want to have this number here, you're going to It's going to be difficult to do it for an explicit sum, but you can always multiply by the common partition function z above and below, and because that will cancel out. What it comes out to do it is just taking the ratio between the probability of all the states that have lambda equal 1 divided by the sum of the probability of all the states that have lambda equal 0. And that will give you the exponential of the free energy. This is stuff that, so it's so fundamental that the more we talk about it, the more I will get in trouble. So we'll move on. So the umbrella sampling protocol is, we know it, of course, from the application of harmonic potential, the reaction coordinate, to restrain it into a certain number. It actually was not even derived as a harmonic potential at the beginning because it was a Monte Carlo simulation. You can check out the paper. It's actually on the classic paper is one that is the most interesting to read. And Krishito actually told me that John Valo actually did not like the term umbrella sample. So take, of course, thermodynamic, so historically that's what we call it, but you should, of course, go and check what was the original intended approach. Of course, remember always that methods that were derived 40 years ago were derived for software and hardware all the time. And now, of course, we use the same theoretical foundations, but our approaches, our priorities may be different. And we may name the same things differently. There's going to be coming up another example of things where we give different names to the same one. Say that we have in the real system the energy function of an analytic dipeptide or a mass protein tells us that basically the difference in energy, not free energy, but potential energy, so we know between the two states that we're interested in, lambda equals 0 and lambda equals 1, is around 8 kcal per mole. I picked the 8 kcal per mole as an example because it gives us a Boltzmann exponential once you divide by the kT for t equal to 300 K, room temperature, it gives us roughly 1 part per million. So the one with higher energy, the lambda equals 1, will be sampled in an equilibrium simulation about once in every million steps. So most of the time, the simulation will only see the, let's say, lambda equals 0. So umbrella sampling really, if you want, is the most straightforward example of an enhanced sampling method. You're just tuning the probabilities of each state being visited. And since it was formulated actually for a Monte Carlo simulation, there was even more than emphasis of changing the probability of each state being visited. So what you can do is basically add the balancing potential. Now, in the Torium law paper, it wasn't necessarily a parabola, but I'm writing it as a parabola because that's what we use most of the time today. And here you can write the parabola this way. The offset is -8, and the coefficient of the second order term is 16. And then basically this term will be equal to +8 when lambda is equal to 0. So basically we'll bring lambda equal to 0 +8. It will bring lambda equal to 1 down by -8. So what has happened then? It means that basically the probability of Boltzmann, the new Boltzmann weight for the lambda equal to 1 is going to be 10 to the 6, but of course, in the new simulation, we're not going to have 1 million times more samples. It just means that it's going to take pretty much all the samples, and the lambda equals 0 is going to be much smaller. This is applying this potential, which we can tune to the energy function of the system, not the free energy which we're supposed to calculate. But since we know the energy function, we know how much we may need to bring up the state. If the energy function is to be evaluated over many states, and then it goes on to be a collection of states, we can do a short trial run that is not going to give us a good free energy calculation, but it's still good enough to get a guess of how much do we need to bring up certain states. And what we do basically is apply this parabola here, which is going to be applied to the each point. So if, for example, you applied here only minimum of the potential and the force, what it's going to do, the problem is just going to confine the system to be there. But if you do it on a barrier, it's going to confine the system to be on the barrier or in the neighborhood of it. Of course, the system will try to slide down, but the umbrella potential will keep it up there. And if you do it many times, you do a lot of windows, like you should always do, especially because there's more cores available today, so you can always spawn more simulations if you automate the process. Each one of these parabolas, if it overlaps, and they should overlap because you want the distribution is for all of them, you can actually pretty much pick out any state you want, no matter how high the energy. You just need to add a biasing potential that is large enough. Of course, you got to be careful that you don't end up with large forces that could break up the system, but you are in control of that. It may be a problem, but you can fix it. And of course, what you end up doing is basically destroying the canonical ensemble. If you're changing any function, of course, you're not going to get anymore what is the ensemble or distributions. And I have a problem which wasn't there for thermodynamic integration. In thermodynamic integration, you can measure the forces. You can always measure the forces that the force field the entire system was doing, but not the ones that you were using to bias the system. So yeah, so you could actually, I mean, can show you later how to practically do it. You can do an umbrella sampling simulation, or use the umbrella to boost the sampling, and then thermodynamic integration behind to measure the free energy. What you're going to do is basically turn on the Uranian code to subtract the overall potential, because you put it on the side, and then basically give you only the forces that come from the system, from the force field. But like I said, if you're doing this process, if you're trying to measure the free energy from the probability distribution, the probability distribution is the one that you can estimate from the simulation using the bias potential. And you cannot subtract it anymore. Of course, you can subtract it from the energy, but you cannot subtract it easily from the free energy because you don't know whether they are in a one-to-one relationship. So what you're going to have to do basically is build a histogram from the one you got that is has the effects of the bias, the effects of the umbrella potential removed. So in the definition of two-level law, actually the reference should be here, that's the classic paper. This boils down to basically, again, taking the sum over the probabilities of the states for lambda equal 1, divided by the sum of the probabilities of lambda equals 0. But, of course, these are the sums in the canonical ensemble. That's the one that you're not simulating. How to relate to the one that you are simulating indeed. The one you're simulating has artificially biased the sampling by a factor W. Say that we bias the sampling for only for the state lambda equal 1. So the probability of sampling the state lambda equal 1 is actually the real probability multiplied by the biasing factor. But now, supposing the formula that multiply and divide by this biasing factor, of course, means doing nothing. What I'm doing is basically we're then taking the histogram of this part, the product of P times W. And basically P times W is the probability in the bias simulation, the one you actually have. What you're left in the sum is that you have the W, 1 over W, which is left there. It doesn't cancel out. But then basically you're saying, well, this basically tells me that what I'm doing is taking the average, ensemble average, for that simulation of 1 over the biasing factor. So if you have a biasing potential of 8 kilopascal per mole, the biasing factor is e to the minus 8, or if you bring if you do your potential is minus 8, the biasing factor is 10 to the 6. So basically, you know that you have to take the average of this factor in take the average of the biasing factor for all the states and take the collection of states. And this is done by techniques that are pretty much established. There's not only one. There's the classic one is the one method that has been used a bit. I think I have to put it in there at some point, the reference to Benoit's paper, the 95 one. That's where he was using one to estimate variances. Of course, with when you're combining probability distributions that come from independent simulations, there's many different approaches to do that. There's a lot of people who also prefer a basic definition of probability distribution because they would rather have this distribution of parameters rather than a confidence interval and error part, which is what you can do with, for example, other bootstrapping methods. So this, you can actually have it pretty much in many codes. Alan Grossfield's one code, which I'm going to link to later, does this. The Chromax analysis tools has both methods implemented. Like I said, this is what you do in the analysis phase once you've done the simulations. You can always try it out later. But should I maybe stop before doing meta-analysis, or?
We have a coffee break in 10 minutes. So if you want to take some
Could you
time.
show the previous slide again? I'm still trying to understand what is the
Let's
difference.
do some questions until the coffee break, maybe, yes.
What is the difference? Like, I'm still trying to understand the difference between the two methods, like the WAM and the.
I'm not explaining it in detail. I'm saying basically that what is done is basically that in the one method, you are counting using the Poisson statistics of the histogram bins. Using the Poisson statistics, you collect bins from multiple histograms, and you bake them into a single histogram. And that is used basically to derive an average, which of course you can always can, but more particularly derive an estimated sampling error. This is, at the end of the day, not very different from using the Bayesian definition where you take a prior distribution of a probability around, which is, assumes, for example, flat, and then you feed it as information the trajectory of the simulations, and then basically you get a probability distribution for lambda that is basically compatible with that. And that is actually done with different compute kernels. I'm not too familiar with the one by Ruby, but that's the one that is actually implemented in some programs that I used. The point is that what the biasing methods do is always the main point in unbiasing Urbana simulations is that you have your simulation where you artificially fiddled with the probabilities. So in the canonical ensemble, this is the formula that you would get. So you have many microstates for lambda equal 1 and many microstates for lambda equal 0. You can do this sum for both of them again. But you no longer have this formula for the simulation you have. The simulation you have does not follow an ensemble that you want. In the simulation that you have that. The reason why I'm not writing it because that will not be the probability, but in the simulation that you have P times W, that's the probability of that microstate. So if you want to relate that to this, you can use this trick of multiplying the pi by tau. And then what you're having basically is this term here, which basically you're sampling with the probability P times W, which is the bias probability, the factor 1W. So you're basically taking the average, ensemble average of 1 over W, but it's the average in the biased ensemble. Most of these methods are basically black box, so to speak. It's really, as I'm going to show in a little bit, the best way is to make sure that you sample the free energy space correctly, and that you will actually look at the trajectory of the simulation. You will, then, once you've estimated that you have sampled enough the phase space, you can use one of the available methods to combine the histograms. And the reason I'm not going in detail into what each method does is that I don't actually propose one or the other. And all of these methods will be convenient and effective, and they always take the same input, they always give the same kind of output. Yeah.
So I have a question about the bias function. So does it necessary to be unique or uniform across the reaction coordinates?
No, you can change. You can have one was introduced for umbrella sampling, but and already in umbrella sampling you have parabolas. Well, you could have umbrellas that are not parabolic. You can have parabolas with different width, and also you could have biasing potentials that are not parabolas at all. One can be used also with metadynamics biases. Of course, you need to correlate always the biasing potential that you have at a certain step. So if you have a metadynamic simulation, you can do one with the bias that is at that point. So if you're doing a metadynamic simulation where the bias changes, then it's not like you have a constant W. The W changes over time in the metadynamics. But you can incorporate that into one algorithm. So basically, every state in the trajectory, you know how much is the bias you put in, and then you can think of it as estimating the W.
The follow-up question is how can we determine the bias function? Does it
How can you choose it? It's basically you should get a uniform coverage of the interval of the lambda that you want. Any function, any biasing function that does that job is a good function. You're supposed basically everything has the purpose of taking you out of the lambda equals 0 state, which is the minimum, and basically sampling also additional higher energy states. So it means that we have an equal amount of sampling in states between lambda equals 0, lambda equals 1, and any point in between. So any biasing function that does the job of giving you more or less uniform distribution is a good bias. Metadynamics is, first of all, a name that we use for the most recent incarnation of one method, which was called local elevation before, was defined by Van Gusten, or conformational fragment was defined by Grummüller. Van Gusten used this idea on backbone torsional angles. Grummüller used this idea on projections along a covariance analysis modes or normal modes as corrected variables. And Parinello and his then postdoc Clio basically extended this formalism to any corrected variable, which was probably straightforward, but in any case, they actually did use it on a variety of problems, not just the two specific ones of the predecessors. But think about metadynamics as all these methods combined. It's basically any method where you apply a Gaussian bias, which is deposited as you go during the simulation. But what metadynamics does is basically taking the idea of sampling, but doing it as a self-discovering tool. There was also an adaptive umbrella sampling, which I'm not talking about, that has to do with defining automatically the position and the stiffness of the parabolas. Another way of basically bumping up the statistics and the sampling of states that are high in free energy and normally the system wouldn't go to is basically adding potential energy to the ones that are low, so that basically if you raise the energy level there, then the system will move to the ones that are high. So I can show you quickly. Metadynamics is great for movies, so you're going to see a few. And this is how it works. So the real free energy is the red one, and you add the bias, which is a Gaussian, the blue curve. The resulting curve is the green one, and basically it will be a resulting sum of the red curve, which is the real free energy, plus all the Gaussians that are being added up to this point. So it depends really on the trajectory. The bias is not chosen from the beginning. The bias is not chosen from the beginning, but it is determined by the states that are visited by the simulation. So hopefully the collective variable reaction coordinate is, well, the collective variable is the reaction coordinate, because most collective variables are not the reaction coordinate. The reaction coordinates are the ones that are good. But if the choice is good, then the system will respond appropriately, and then will basically move from the global free energy minimum to a local free energy minimum. Or in any case, if you started in a local free energy minimum, you will go to another one. Now this is going to add some bias, and the effect of this bias is raising the energy level. I'm going to speak loud, so at least if the voice comes through.
Goes down.
Yeah. So if the energy level is raised, then basically, of course, you should be careful that you don't exceed too much. But if you don't run for an infinitely long time, and especially if you don't use big Gaussians, if you don't use a big bias, of course, I think you intuitively understand that more bias in general is bad. You should just use just as much bias as you need to see the states that you're interested in, but not more than that. More bias is good, so less bias is good, but basically the intermediate effect is that it's going to end up flattening the landscape. Now this landscape does not look flat because the Gaussians that I've added are big. But if you add small Gaussians, since they're always going to be deposited on the new minimum of the free energy, in the end, you basically end up canceling out the minimum. You end up filling the free energy landscape. Probably you've seen Metadynamics movies before, so I shouldn't indulge into this one too much. I'll show you what is the correlation between when you use the method with appropriate parameters, so small enough Gaussians and slow enough steps. Basically, what you end up doing is raising again the free energy of the system. This is this is the trajectory that the system does over time. So that's what is important, more so than in umbrella sampling or in thermodynamic integration. ABF, also like metadynamics, is important instead. But the methods that I've talked about before today relied on basically setting umbrella windows, so you knew where the collective variable was going to go, because you put it there, you put a biasing potential that was going to explore that region selectively. And if you needed another point, you did another simulation. With metadynamics or ABF, which does the same thing as metadynamics in the force space, what you're doing basically, you're letting the variable explore everything, and it's actually trying to boost the sampling of the states that are not visited. So it's especially useful in metadynamics particularly, or in ABF, to look at the trajectory of the collective variable. So let's look again at this movie here. I'll leave it here as it's played out, and I'm going to replay it once. So basically, we started off in the B minimum, so the collective variable was 1. So we were here. And the system stayed there for a little bit, until it added enough Gaussian bias to come about to this point, if you remember. And then it jumped over the barrier, because the barrier was still there, but it was small enough that the thermal fluctuation brought it over the barrier. And then it started looking at another minimum. Then it had a jump here, and then it went to the second minimum again and stayed there. And then it kept adding bias in both minima, up to the point when basically here it added enough bias that the minima didn't exist anymore. And then it just started going back and forth in an almost diffusive way. The slight problem with metadynamics is you keep adding these Gaussian functions, you keep adding a force which will depend on time. It actually depends not only on time, but also on the trajectory, basically. So you're not in real diffusion anymore. So if you've seen, did Chris mention that at the end of ABF, you should have free diffusion? In metadynamics, that is almost true. It's not completely true because metadynamics keeps adding a bias, whereas ABF tends to a constant bias towards the end. Once ABF converges, the free energy is flat, it will stay that way. With metadynamics, you will always add a little Gaussian hump, and that hump will help diffusion a little bit. So diffusion is not going to be real diffusion metadynamics, but it's going to be sort of like diffusion, and it's going to be relatively fast. So you can see some sweeps, or in any case, some uncorrelated movements of the variables going across minima because the minima don't exist anymore. So if we wanted to look at the trajectory here, you could say that somewhere about here, and this is just eyeballing it, but you could use whatever analysis you want of the trajectory afterwards to say, well, this was my point where I could say that the free energy was sort of converged because you filled up all the free energy with the meta-dynamics bias. You could theoretically say that collect the histogram of the corrective variable from this point onwards, and if it's flat, then it means that the variable, the bias had converged, because then once you have add enough bias to cancel out all the minimum, the variable will go everywhere, the histogram will be flat. If the histogram in the last portion of the simulation is not flat, maybe you can make it a little longer. But in this example, this was long enough, and you can actually convert to the free energy. Now, the bias here has added a lot of stuff, but you can see that there are some ripples here. There's maybe techniques maybe to remove them, but if you use small enough Gaussians, they're going to go away. But in general, what you do at this point, after you're saying, well, at the end here it's converged, here it was sort of converged, and then let's say that here it's really converged for good. At this point, you just take the biasing potential of meta-dynamics as it was evolved up to that point, and then you flip it, which you've probably seen before, with the reversing sign. Because at that point, if you know that the free energy of the system at the end is flat, and you know how much bias you put in, then of course you subtract the bias from a flat constant, and then you will get the free energy. So that's the assumption. There's there's a lot of versions of meta-dynamics which we can talk about. Some of them are implemented in NAMD, the most common ones. For the most advanced ones, you also have the option of comparing dynamic with Plume or using other versions of the software where there's more variance on meta-dynamics. There's been like 2 papers with the 1 new meta-dynamics methods every year since 2005, 2006, so there's a lot of versions. I'm going to basically outline the rules for the very basic ones. Basically, once, as I said, when you're adding Gaussian functions, basically you're always adding a new bias, which is not going to cancel out. Again, in ABF and thermodynamic integration, you're measuring the average force in each grid point. If the simulation goes on longer, each grid point will have more statistics, and that number will converge to a number, to a constant. And then you integrate that constant, you will get the PMF. But in meta-dynamics, things are not constant. The bias will keep changing, and you will get some ripples at the end that will be due to the meta-dynamics bias itself. How to remove that is not easy because this is not an average over the canonical ensemble. The meta-dynamic simulation has its own ensemble, but it has been proved also with rigorous statistical mechanics that you can obtain the free energy by doing the subtraction. But the problem is that, yeah, you have still these ripples. So practical thing is maybe like run multiple simulations and take the average, but that means that you have to make sure that the whole converges. Or maybe if you have a long simulation, well, you can also do more simulations. But after it has converged, you can just take the average at different times. Because if the Gaussian is basically just noise, they will create a ripple in the free energy that is not really there. If you go and look at the same PMF 10 or 20 nanoseconds later, that ripple is not going to be there anymore, or it's going to be compensated by another one. The things that are noise will cancel out when you take the average. So it's a very practical approach to take the average of the PMFs at different times, for as long as the times come in this region of the simulation. If the trajectory looks like it's still looking at different minima, wait. But after you see that the simulation is exploring everything, then you can say, okay, at this point, the bias has canceled out all the free energy minima, and now it's just a matter of getting basically the little ripple down. So you can take the average of what comes in the second flat. Yep.
Are the Gaussians added where it's in the coordinate space? Is that where the Gaussians are added?
Yeah, they're added in the space of the collective variable. So it's a potential that acts on the variable.
Right. So it's in that location, and then you add the Gaussian until it moves out, and then you add the Gaussian to that.
Yeah,
location.
exactly. Like, I mean, it's this is why I showed two movies. This movie comes from my friend Fabrizio. The crappier one is mine here. But the reason why I still kept it is that I'm showing it here. I can play it. No. I can go back. I need to go back to the point. Oh, here. Okay. So here, I'm showing explicitly the Gaussian function. So you know that potential is going to be added, and then it's going to stay there. Of course, I'm showing just the last one. But the point is the potential gets added on the states that you visit during the simulation. So until you converge, there are no two methodynamic simulations that are going to be alike. You could say that for an assembly simulation because the bias is constant, so it's not a matter of converging. But in methodynamics, there's a transitional phase. The same thing happens in ABF, and I'm sure Chris has mentioned this point. There's a transitional phase where the simulation will just do something that may not be the same thing as some other person's simulation. So two unconverged methodynamics or with ABF simulations will look very different in the trajectory. Yep. Yep. Sure.
So, because it keeps adding Gaussians, do I really see after convergence, do I really see a flat histogram? Because Gaussians will keep getting added, right?
Yeah. So you wouldn't see a flat histogram from the beginning, because in the beginning, you started the.
So my question is, since when you said how it compares with ABF ends with a flat potential.
Yeah.
But this one does not. So how do I expect a flat histogram?
No, they both add with the. So we were talking about potential, like as a total potential. So there's the free energy of the system, which is not an energy; it's a free energy. But let's say that from the point of view of the collective variable, it's an energy. And then you have bias, and then you end up with a constant free energy. Both ABF and methodynamics will converge to that situation. Both also remember that if you started from the beginning, in the beginning you started with no bias. So you were visiting more the states that corresponded to the minima. So for a long time, you're still going to have more samples for those minima because you started from there. The statement about flat histogram is the same for methodynamics and ABF. And it only matters for the region beyond this point. Because at that point, the minima have been cancelled. So if it's true they have been cancelled, then the histogram needs to be flat. So the histogram needs to be taken for the last part.
But so if the algorithm stops adding Gaussians at that point or no?
No, it continues doing that. That's the difference between ABF and methodynamics.
That's why my question is, how do you, if it keeps adding Gaussians, how do you end up?
Well, exactly. You end up with something which is flat, more or less, but the more or less is just noise, which will basically cancel out over time. What happens basically is that you keep adding Gaussians, and then you keep adding Gaussians uniformly. So you keep adding energy, but you keep adding a constant to the entire PMF. So if you add a constant to the entire PMF, you're not changing it.
Does the size of the Gaussians change throughout the?
No, there's some methods where you can tune the size of the Gaussian, so the height or the width. I'm going to mention about one of them, but yeah, there's let's understand this point, and because really, unless you do something artificial, methodynamics does not converge to a constant bias; it keeps adding bias. Versus IBF naturally goes towards no bias. I mean, or towards a bias that doesn't change over time. Methodynamics, by definition, changes over time all the time.
by adding potential of energy to it, so does it mean that by practice, MD is modifying the force between the atoms? And
MD or?
I mean the program,
Yeah.
the MD program itself is modifying the force between the atoms in order to add this potential to it.
I'm not sure I understand the question. Is more defined or?
So I just asking it practically.
Okay.
How
Or
is
technically,
this
how to implement it?
potential?
So,
I think his question is, are the forces being modified?
no, the forces from the potential of the system, from the charm force field, the Amber force field, whatever you're using, are not changed. ABF, umbrella sampling, state MD, metadynamics, they do not change the Hamiltonian of the system. If you're referring to, and somebody else mentioned it before, to maybe accelerated MD by the McCammon group, where you artificially change the force field to boost, that's another story. That's a situation where you start off with a simulation where you change the force field, you do it in a control way so you can recover the correct statistics using some techniques, but it's not like a method like metadynamics or MDF.
So it's like pushing the system towards the reaction coordinate in some direction.
Yeah, all the methods that I'm talking about here add an external force. They do not change the force that comes from the molecular dynamics Hamiltonian. So of course they change what is the total force experienced by the atom. They change the trajectory, but they do not change what the physical model looks like. Because they are supposed basically to add a bias to to boost the importance sampling of states that otherwise you wouldn't see in a short simulation. But they're supposed to do that in a way that the thermodynamic will converge. And then the results of that should not depend on the method you use. They should depend only on the force field that you use. Yeah.
When you're saying, I'm following his question. So when you're saying keep adding some Gaussian potential, do you mean that you heat the system?
Yeah, that's an excellent question. With any method where you add the bias, you add extra energy, extra potential energy, which eventually will get converted into kinetic energy, so heat. The fact is that you're assuming here that the system will relax, so it will act, it will react to the change in potential energy, and basically will converge to the new minimum, but then converge to the no free energy minimum, which means that the atoms are going to acquire kinetic energy, but they're going to exchange this kinetic energy with the thermostat so that they can keep at a constant temperature. But if you're not doing that, if you're using a bias like thermodynamics or ADF, which is time dependent, in an NVE simulation, constant temperature, but constant energy, sorry, you're not going to end up with a constant energy, you're just going to keep increasing it. And the temperature, of course, too. Because then, of course, the system will, if you keep adding potential energy over time, the system will convert some of that into kinetic energy and heat. So yes.
So do you mean that temperature of the whole system would keep increasing?
No, because if you're running it with a thermostat, the kinetic energy, the excess kinetic energy that some atoms have is going to be given to the thermostat. And then if some atoms are cold, the thermostat is going to give heat back. That's how a thermostat works. But the point is that, the thermostat has to do this on a time scale which is faster than the biasing potential changes, which is typically the case. Because if you want a nice free energy, you want to have like a very small fraction of KT for over the time that it takes to decorrelate the variable. That time is never shorter than a few picoseconds. So in a few picoseconds, you have exchange cycles with the thermostat, no problem. But if you use like a coupling time with the thermostat that is really long, because for some weird reason, you shouldn't do that. But if you're using a thermostat which will exchange heat with the system at a rate of microseconds, then yeah, you're going to have problems. Because then the biasing potential will add heat, and that heat will not get dissipated instantly. So then the method assumes that the heat gets dissipated quickly. Any method, meta-dynamics included, assumes that heat is going to be dissipated quickly, and then every time we'll find a new free energy in it. But that's typically the case for thermostats. Like we'll say, in addition to that is that there is not only heat, other variables are other potential energy variables, there are other degrees of freedom. They're not the lambda that you chose, like hidden collective variables that are important because your lambda is not the reaction coordinate, but only part of it. It's actually a more complex pathway that you can always model with way one variable, but you know what it is. So if you're taking lambda that looks so right, but it's not quite the one, you're going to get a projection of the real reaction coordinate onto the axis of the future. What happens when you neglect other parts of the reaction coordinate because you don't know about them is that these variables that determine large parts of the potential energy will not relax quickly enough for the method to do its work. So I would say, yeah, maybe you're right to bring up the point of the dissipation of heat. And I think it's a good analogy to use heat to understand the effect of slow degrees of freedom. Like if you use the relative variable, it's not the good one because you neglected some slow degrees of freedom that you didn't know about. That's very similar to not giving the system enough time to thermalize to the room temperature. So, okay, I mentioned that once you are in the converged phase, you can take the average of the meta-dynamics PMFs. You can always take the average of ABF biases at any stage of the simulation because it always adds up. But for meta-dynamics, this quite doesn't work. It only works after you've reached convergence. So be mindful of monitoring the trajectory to realize when you've reached this stage. One, you mentioned that. Can you actually make the Gaussians converge? Well, you can. One method is the well-tempered meta-dynamics. I'll show the reference there, but it's definitely in the documentation. Well-tempered meta-dynamics basically takes down the weight of the Gaussian over time, or more precisely, it brings it down in proportion to how much you high on energy. So it's basically an energy cap. So the bias gets smaller and smaller, and it doesn't add more than X megacal per mole. This is nice because it protects you from putting too much force on the system if you keep running a meta-dynamic simulation. As I said, once you are in the converged phase, you will keep adding bias uniformly. You will basically add a constant to the PMF, but you're going to raise the energy level. And maybe you will find other minima that you totally didn't know about that are over a huge barrier, and then the system will climb over the barrier and just precipitate. You can understand that if you add like 100 kcal per mole worth of energy, you may actually get out of a local minimum that is going to destroy your system. So well-tempered try to obviate that. The problem with it is that you're choosing ahead of time where to cap the energy, the free energy. So that's an additional thing that you should know about. But also the fact to remember is that when you're running a simulation and you're decreasing the size of the Gaussians, basically you're decreasing the importance of that simulation frame in the trajectory. It means that what comes in the later stages of a well-tempered monetary dynamic simulations is less important than what comes at the beginning. And I would say that maybe that's not great because it gives too much importance to the initial stages of the simulation when the system probably wasn't even that much relaxed. And it decreases the importance of the final stages of the simulation. So we'll say if you want a system that actually converges to a constant bias, that's ABF. Meta-dynamics will not converge to a constant bias, but like I said, it will converge to a constant bias plus some noise. If you can deal with that noise appropriately, you're good. So mere temper is an option in many codes, including MD, but you can use it, but keep in mind that what you're doing is basically choosing when the simulation will converge ahead of time. So you have to know a lot to be able to do that. And there's other approaches. I mean, I'm not talking about reconnaissance metadynamics, funnel metadynamics. There's other. The funnel metadynamics is custom restraints. Multiple workers and replica exchange metadynamics are actually quite open a whole new set of variables because they add multiple replicas to increase the sampling, and they even exchange multiple metadynamic simulations, the bias exchange by Lyo and Piana is pretty neat because it uses many low-dimensional metadynamics biases and exchanges between them. These methods never hurt. I mean, there's multiple workers implemented out of the box. Replica exchanger, you can do some scripting, but you can also enable replica exchange metadynamics in MD. And it never hurts to use them if you're like making sure that they work in the way they were intended. You're not, in a sense, changing what the PMF should look like. You're not deciding ahead of time, you're just adding more stuff. So the main thing that I would say that is important for any multiple replica method metadynamics, probably other methods too, is that you have to make sure that the replicas really go around on their own and cover the phase space independently. As I was mentioning to some of you during the break, in a multiple workers metadynamics, if all the replicas end up in one minimum, then it's no different than to add basically, say 10, if you have 10 replicas that all end up in one minimum, it's no different from using one replica with the Gaussian 10 times big. For the multiple replicas methods to work, they have to work in parallel, so they have to work on different things. They have to work on different regions of the PMF. There's no real metric to make sure of that because who decides how far in the space are you? That depends on the units of your collective variable. That depends on the shape of the PMF. So you have to look at the trajectory. But if you see that if you have a multiple replica metadynamic simulation, all the replicas should look like this, and then it should go about a different way. And they shouldn't all pile up at one point. But when you're starting multiple replica simulation, of course, each replica doesn't have enough bias to go out the minima, so they should all be in different minima. You should have like ideally as many minima as the replicas, so that each one is doing their own thing, and then they're going to cover everything in parallel. Yeah.
Is there some sort of selection mechanism? So say you have two minima, but one is either much shallower or much smaller, and so like the possibility of replica falling into a second well with another one. I think Amber has worked on a selection where if you have, say, 5 replicas in a well and then 2 exploring like another surface, at some time step it will give a probability of locating one replica to avoid the other. So there's some sort of like selection where you don't have like all your replicas exploring a single well.
I mean, the simulation evolves over time, and the PMF depends on how much. So it really depends on what is the decorrelation time. I can say for sure that if you have 5 replicas in one minimum and 2 replicas in another minimum, and if none of these 7 replicas leave, then that gives you the free energy.
Right.
There's going to be 5 replicas putting Gaussians here, 2 replicas putting Gaussians here. That's going to determine the free energy difference between the two of them. So you really have to make sure that they travel, the replicas travel. So if the correlation time for the corrective variable is slow, doing multiple walkers or exchange, to some extent, exchange goes around this problem in another way. But basically, you don't get around the problem of the slow correlation time by adding more replicas. It definitely can help you by boosting statistics so that, especially if you have a very broad free energy landscape, you don't want to cover it sequentially. You want to do it like in the umbrella sampling way so that they work independently. with metadynamics, you cannot stitch together individual PMFs. You have to couple them to a protocol like multiple walkers or replica exchange. So a way of reconstructing a very large landscape is to use one of these. But like I said, yeah, they have to be spread out in all times. I'm not sure if somebody, probably they've done, there's a lot of papers to read about it. They probably introduced maybe some bias to disclose replicas from coupling together, but that's tricky again because you're
you're introducing like another degree.
Exactly. Okay. The last one, maybe I'll go over quickly because it's also supposed to be done quickly. That's the non-equilibrium work. What's nice about this is that the STLMD protocol is typically used together with the Jarzynski Ferenc estimator. So that was also in Chris's slides 2 days ago. What it does basically, without going to the derivation, but it's such a relatively recent paper, so you should read it, is that there's an average here that is taken of an exponential of the work done by the simulations, and then basically the frenzy is correlated to that. Why do we have W here? Why do we have work and not energy or free energy? Because by construction, it's assumed that these simulated experiments or real experiments are going to basically work against the system, and this work will not always give a relaxed distribution. There's going to be some point along this path where the system doesn't really fully relax. So the Jarzynski theorem says that you can collect many of these simulations, and if you take the average of their exponentials, not take the average straight away, but take the average of the exponential of the work, then you can get the exponential of the free energy. Because the point is that the non-equilibrium work will always be an overestimate of what you need to put. So this exponential will favor the lower amount of work that's taken. So we'll artificially skew the distribution of the simulations of the replicas that they do less work. This is a part thing. This is best understood using, again, a slide that I'm reusing from Fabrizio, where basically you see the trajectory over time. Now again, it's a time-dependent bias like ABF or metadynamics, but the time dependence is chosen ahead of time. You're using a harmonic potential, a spring, and you're just moving the reactional coordinate from this minimum to this minimum, and you're doing it basically over time like this, using a set trajectory. The problem with the set trajectory is that you dictate exactly how the process should go, and it should go into a set amount of time. So this is good to schedule how much time you need ahead of time, but then you're assuming that it will converge within that time. That could be a number destroyed. One problem with it is that, intuitively speaking, when you go from here up to the transition state, you're performing work to bring the system over the barrier to add enough energy. And that work is definitely going to be dissipated away. If you generate heat, is going to be dissipated. But again, if you once you go from the transition state to the new minimum, then you should get that work back if this is the real PMF. In this particular case, you don't quite do that. You end up at almost 2 GeCal per mole higher than in this case. Of course, you can run slow, and you will converge to the real energy. But this is an example where basically you put in enough work here. There's also here it's 6 kT instead of 4, so it's not really the barrier you were expecting. And also here you get 2.7, almost 3 kT instead of the 0 difference on the original. If you're choosing the path, you're basically being very picky about what the simulation should explore, and the system will do its best, but maybe these slow degrees of freedom that you forgot about are not going to have enough time to relax, because you keep the main variable that is coupled to them constrained, well, restrained, but You know that NMD uses constraints and restraints interchangeably, and then you go basically down, and you don't necessarily equilibrate over time. So state NMD will work. The statistical formula will work to combine multiple stimuli experiments. Make sure, of course, that you're not doing too much equilibrium. You can, of course, use non-equilibrium model as an information about pathways to classify different pathways, and Mahmoud is going to talk about that on Friday as well. So you can still use TSTMD, maybe not to compute the energies, but to rank different quantitative variables and pick the ones that are best. And well, this is a very general recommendation. I talked about one-dimensional stuff so far, but of course there are always hidden variables. If you cannot figure out the one-dimensional variable that really sums them up, just use two of them and do two-dimensional. And because as often you neglect, if you neglect a relevant variable, if you want to go from here to here from a straight path, you're neglecting the whole other path in the other dimension, which is important. And so it's always basically, again, this is now best practice at part, not much more formalism. The problem is always that it is a hard problem to find out the reaction coordinate. You want to get thousands of degrees of freedom into one, and sometimes, okay, you get lucky or you're smart and you do it correct. Most of the time we're lucky, and sometimes we're not lucky. So sometimes we're not lucky, then well, at least we live in an age where we have a lot of computer time available, but not because everyone has a ton of computers, but the computers are having more cores, and now your phones have 4 cores or more. So you can also run more replicas. And particularly if you run more replicas, then you can sample more, and higher dimensional energy landscapes are not necessarily that demanding. They used to be back in the day, but now 2 or 3D can do. But no more than 4 or 5 dimensions, please. Because already plotting it will be tricky. With 3 or more, yeah. And one thing that is a guideline, but is not a strict rule, is that it is probably the most straightforward thing to do multidimensional calculations with probability-based methods, because then you're talking about doing multidimensional histogram, which is very natural to define. So for umbrella sampling, metadynamics is very easy to do that. With ABF, you can also do that, because of course, if you measure the free energy derivative in one direction, you can do it in another direction, you get a free energy gradient. But there's an additional considerations to be done, I think Chris will talk about. If not, we can mention it during the exercise. And finally, notes about implementation. So we're talking about NAND here. Of course, we always talk about many other medians, but that makes the slide much easier. Thermodynamic integration is used in the context of geometrical transformations or chemical transformations. Both the Colver's module and their chemical module and MD use thermodynamic integration to split out free energies. FEP is mostly used by their chemical module. For probability-based methods, umbrella sampling and metadynamics or any of the post-processing tools, you can use, well, you can apply a bias to Colver's. Classically, you also use TCR forces. There's a lot of collective variables, and especially a lot of videos on metadynamics improved if you can make it work. Generally, you have to compile because it's an add-on that will not make possible to compile NMD everywhere. But if it works on your platform, that's an additional tool that you can use. And the same for Jasinski. These tools can basically give you access to many methods that do this kind of things. And I think this. Okay, yeah. About the Federici method, basically, my main recommendation would be to pick a method that will give you higher reproducibility. That is as straightforward as you can manage, as detailed as you need to capture the subtleties of the system, but you have to be able to do the same calculation twice. If you get different results from the same calculation twice, you're not doing a great thing. You're probably victim of statistical fluke. And you can try, for example, to replicate one that was done study from the literature, but be aware that you may have differences that have a lot of noise, even for the same system, for the same protocol. And the statistical flux can be either yours or theirs. Don't assume always that the paper was always run with the Faraday calculation that was fully converged. We try to make it that way. Peer review is trying to be rigorous, but truly speaking, these methods are difficult enough that even the person running them does not necessarily know for sure whether they're truly converged or not. So always be mindful about the fact that statistical flux can give you either the wrong result or the right result, depending on just out of chance. And one thing that I also recommend is that you make your protocol automatic or automated, because now you have multi-core workstations, and or you can also request more time for clusters. Of course, if you have less time, of course, you're going to choose the tasks. But it's less of a problem than it used to be years ago to get more processors. And to run on more processors, just make it automated so you can save your own time. So you may want to choose ahead of time the method you're using, so it requires less maintenance on you and more automation you can just run it through. And one thing that is really the big question, there is no conclusive evidence of one algorithm being always better under all circumstances for all types of systems, for all types of collective vehicles. They all have the pros and cons, and the limitations I assume they are evident from the presentation because they've all measured different things. Thermodynamic integration requires the forces at runtime, requires a code that is enabled to take the forces and compute the projection on the collective variable. Doing like a Bennett state restoration analysis after the fact, you can do it whether you use the NAMD or whether you run a simulation with another code. So some methods are more flexible than others. And some methods, of course, use different things. For a chosen problem, you may be in a situation when, because you're measuring a different physical property, the force, the energy, the probability, for a particular simulation, that property may converge faster, and one method may actually be better. So for a given problem, it is worth taking a look at whether one method is better than the others. Knowing that there is no general rule, but for your system, there may be a method that is better than others. And of course, it really depends on you getting to understand how the system works and what specifically each method uses to compute different functions. And if, of course, you don't want just to pick, perhaps you can always combine different methods. So this is one thing that is actually a new feature in the version that you have for this workshop, not in 2.12. It was always possible to do. It was always possible to apply a bias from umbrella sampling, metadynamics, from a harmonic potential, and measure the phase derivative from thermodynamic integration on the side. So you can get one PMF from the probability and one PMF from the force using different approaches. The way it was done up until recently, you would define an ABF bias with the bias off, just doing the thermodynamic integration part. With the changes in the NAMD structure, we cannot do that necessarily anymore unless you do some tricks. But one option that you have is you can turn on the thermodynamic integration free energy estimate in umbrella sampling or in metadynamics. So then you get two PMFs, one that comes, for example, from the Gaussian function of dynamics, and one that comes from the thermodynamic integration. And like I said, some methods, in some circumstances, may be better than others. This is the PMF of along the distance between a sodium and a chloride pair of ions, and it is from the same simulation. One PMF, the red one, comes from summing together all the Gaussian functions. And there's a lot of ripples, but this simulation was short enough that you didn't have like a lot of sweeps. So, like, of course, you can always run it for longer, convert faster. But as it turns out, the PMF from the thermodynamic integration was already converged. So in this case, if you can add this to your simulation, you have two free energy estimates for the same simulation is always better. You cannot always do this combination, but when you can, do it. I have to caution that this is a particular case where it happens that the thermodynamic integration is better than the metadynamics one. There will be other cases where this is not. But like I said, having the freedom of choosing to put together, try different methods, and using different methods together can be helpful. And I think for the part about methods, this is pretty much it. And I'm going to move on to basically more practical notes about how to use them. So before I move on to the practical notes, any questions about, yeah?
So you were showing that for metadynamics, you need the Plumed plugin, but doesn't the current version of NMD already have?
Right. The difference is that the current version, the one that the metadynamics that I wrote, has standard metadynamics and well-tempered, but and multiple walkers, and with a little trick also bias exchange. It doesn't have some other reconnaissance metadynamics with a recent addition. I mean, there's definitely other algorithms that are not implemented, so are implemented by Plume. So you can add Plume, you can use them today. Some variables are provided by Plume, they are not provided by Corvus. The other way around is also true. You should, in general, pick the one. It's easier, of course, to use the Corvus-based ones because I made the effort to make it integrated into NumD for it. You take a little work into running Plume, but it may be helpful because you have more algorithms there, you have more options. But metadynamics, the NumD that you download from the website has it. Eric? I thought you were raising your hand?
Oh yeah, I just didn't see where you're putting. You mentioned avoiding statistical flukes. Any guidelines of how to make sure that you're not involved with statistical flukes?
I mean, the general guideline is just running the same calculation twice. If the two simulations give more or less the same results, then you can combine them together and get even more statistics. If they give completely different results, maybe you are looking to running both of them or at least one of them longer. On a general basis, there isn't really much more I can say. Definitely, my point is that there is a lot of literature and there's a lot that gets reviewed, and we'll try to do our best. You probably review papers too, but sometimes you must understand, especially in a paper, there's a lot of different techniques, and free energy being one of them. It may not be possible, but neither the authors nor the reviewers knew that maybe the simulation wasn't perfect, especially with the older papers. So be mindful of that. Don't always blame yourself. I mean, start from blaming yourself, honestly. But don't insist on it too long if you cannot reproduce results from the literature, unless really it was clear that they were so long that they were guaranteed to be converged. So the second point is a lot shorter, and because I'm planning on moving as quickly as possible to actually showing some input file generation. So we're going to talk about the Corvus module, which is the main driver for geometrical free energy calculations in NumD. So the name is generic precisely because it implements these techniques differently. Thermodynamic integration, ABF, metadynamics, number of samplings. They can use the same code base for the collective variable and just use a different piece of code for the algorithm. So if you know that if you are comparing umbrella sampling and metadynamics, you know that really the difference is in the method, not in the implementation of the variable. So these are the methods that I mentioned straight out of the box. NumD is a highly scripted program, and we can do more things. And you can do, for example, well, actually, these are, for example, the string method in collective variable space. Chris is going to talk about it. Oh no, again, but you mentioned it before. And this is one example where you use the TCL scripting combined with the C++ code of Corvus to achieve a very high dimensional set. Basically, the code is just designed to implement not everything under the sun, because it takes time to write these functions well, but trying to implement the most general methods that you can use to escape the parameter engineering. And of course now comes the point again, which corrective variable do I pick? And this is really your job. It's not mine, or you can be also your job of your collaborators to help you with that. But basically, what we can help you with is giving you examples of what you can use. And then you will decide in your system what will work best. So one option that Corvus gives you is basically picking a function that is implemented there. Distance, of course, every code has. The hydros, yes, because you have to do Allen in Dagger type. So you have to have the hydros implemented. An RMSD variable is another option. It's less trivial, but it's pretty standard. There's other variables that are a bit more complex, but not too many of them. So you just pick the function that you want, and you say in the code, this is going to be my corrective variable. It's going to be calculated this way. And it's already implemented the derivatives and hopefully also the inverse derivatives that give you the thermodynamic integration and implemented. You can customize it. So Corvus is a code that is available in NAMD, LAMPS, and the VMD. And so you can use the same syntax in all three programs in the units that the programs have. What this is maybe one thing that I want to emphasize because I presume that you're going to be doing calculations also with Prune that does a lot of the methods that I talked about. The difference there is that Prune uses its own units. You can specify to be the same as the one of the host code or not. Corvus always uses the units of the host code, so it's more like an extension always of the host code rather than a standalone program that runs on the side. So one thing that you can use, because NAMD is, like I said, highly scripted, there is an option to customize things. So there's several corrective variable types. The ones that you can actually use are a lot more because you can customize them in different ways. Just like in NAMD, there's the C++ code and the one that once it's compiled, you can use it. There's a gazillion more functions, scripts that some of them are distributed together. Most of them are not, are like plugins or stuff that you can grab from the internet. But basically, the NAMD code base is like a combination of these two. The same for corrective variables, you have the ones that are already implemented in C++. They're going to be reasonably fast, not always, but most of them will be okay. But yet, of course, you can change the way you do. So you can do, for example, a polynomial of different variables. If I want to take the asymmetric stretch for like a chemical reaction coordinate, you can do difference between two distance functions. You say define two distances, then you can say I want a coefficient of 1 for the first, minus 1 for the other, and that's it. And you can also choose the power to give it. Recently, this is again not in NAMD 12, but in the nightly build that you also have available here for the workshop. There's the option of extending this to a lot more functions. Use the Lepton library by Pierre Eastman, who's the developer of OpenMN. He was smart enough to write this as a library. This could be actually drafted as part of NAMD. It's part of NAMD standalone, and then Corvus uses it, but also other parts of NAMD could use it as well in this picture. So you can calculate functions of the variables. You can write these functions in the file. So if you say that your variable is the RMSD, so if you use an RMSD function, you're saying that your variable is an exponential of minus the RMSD. And it's reasonably fast. What you can also do even further, you can do more complex stuff that is not in the Lepton library or in the Corvus polynomial sort of position code. You can actually write a function completely from the scripting language, TCL, and Python is going to be added soon. Python takes a bit more work because it will also have access to the data structures in there, and will actually be more efficient than the one in TCL. But basically, you can write a function of existing corrective variables, or even more directly of the Cartesian coordinates. So you can really write your own corrective variable from scratch. Just remember that if you want to do biasing, you have to write the function that calculates the variable, and the function that calculates the derivative. That's the price of these things. And of course, you can always extend the code. The Corvus code base is on GitHub. So you should definitely submit code there to modify it. In NumD, it's a little bit more difficult, but it has been all simplified recently. You can submit code directly, but I ask, because Corvus has its own repository, that you actually submit modifications there. Some people leave it already, I can show you later. One caution, because that I need to give you, is performance. We're now at the point where CPUs have stopped becoming faster, or at least CPU cores, and then modern CPUs just keep adding more cores. You can now get an 18-core Intel or AMD CPU for your desktop for a relatively small price. Not high-end consumer-grade desktop computer gaming. You can run a cheap nerve simulation with on 18 cores. So of course, these methods need to be efficient and scalable. A lot of these variables are not, because the atoms are used simulated by NumD on different cores, but the variable itself, in many cases, is calculated on one core, and that will become a bottleneck. So make sure you take that into account if you pick a variable. How many atoms do you pick? Okay. So this is a test case of the 8.1 system where I'm taking a very dumb variable, basically the distance between the central mass of the protein and the central mass of the liquid. It's about 10,000 atoms in total, probably, out of 80,000. So it's a significant fraction of the system that is used to calculate the corrective variable. And all this corrective variable, well, it could, for example, be calculated with an older version, but that, I caution, it will be quite small. The code will scale well because it's fast on a single CPU, and then NumD will do the hard part on the parallel. But if you shove too many atoms, they may be too slow, especially for an older version of NumD. This is strictly a technical detail, but I really encourage you to upgrade. If you're using NumD 2.9, well, shame on you. 2.11, okay, I can understand. 2.12, just make the effort of using that because really there's been some performance improvements that are technical, but will help you even if the variable is not parallelized. So the updates are technical, we can talk about them. One thing that you want to take into account is some variables, if they're defined on centers of mass, from NumD 2.12 and later, they offload the calculations of the centers of mass to NumD, and then this is done in parallel. So they're actually quite scalable here. And basically, if you have a distance between two large groups like this one, this system, the distance between the central mass of the protein and the protein membrane, should scale relatively well with NumD 2.12. And if the system is huge, there may be other problems, but if you're running like a corrective variable calculation on 500,000 atoms, and 500,000 atoms are part of the variable, the other problems there. So there's a flag which is on by default, but you can turn it off to basically get the old code if in case you want to test. And for many of the variables, it doesn't make a difference whether this flag is on or off. And one thing that may help you speeding up the calculations is to use different processors of the first node. Like I said, the atoms that make up a corrective variable are gathered by NumD into one place, into one node, and then the variable is computed there. Now you can run the calculation on a single core, a single CPU in a sense. But since many nodes now have many CPUs that share the same memory, you can also parallelize this. If you have many variables, this is done automatically. The variables are being calculated in parallel, and then even if you're running a very large system, but the first node has a lot of cores, and if you're using a lot of variables, then these variables are going to be computed at the same time concurrently. If you're using a single large variable, that's a bit more complicated, but you can get into that situation by chopping up the variable into different pieces and then putting them together using either the sum or like another function. If you use, for example, the radius of gyration, which is not parallelized, you can actually define partial sums of squares for different atoms in the system. These are going to be computed in parallel. Then what you need to do is basically taking the square roots of the sum of squares to get the radius of gyration. But then you can do using the custom function method. So you can actually parallelize over threads, something like this. I have to acknowledge here now, before I move on to demo and then running out of time, all the people that I collaborated with to develop the Converse code. By far the biggest one is Jerome, who has written originally a code for ABF. It was TCL scripted, so not as fast, back in 2004 with the Chris Shippo. And when we met as postdocs in my client's group, we actually merged a metadynamic C++ code that I was working on at the time and ABF code to give you Converse, and hopefully you will find it useful. Of course, we have had support from Jim Phillips and John Stone, the most senior hackers. Chris Anderson, who's now here a part of the URC group anymore, and Klaus at the time, and he was really supportive at the beginning, and it's we're still like sad from not having him anymore. Chris, I noticed here that he's part of two institutions, and including here, collaborators in Tempo, who Axel mostly works on labs, and he has been really helpful in interfacing Converse with that program as well. And Mike has been overseeing in a very high altitude fashion. Giacomo has done a lot of interesting code, and there's a lot of people that are now mentioning that have contributed either C++ code, which in the case it was part of the department MD, and you can use it too, or scripts that you can either use because they posted it online and you can ask them. And so anyone who made changes to the code, if they could do it, then it was great. More recently, I started collaborating very often on a continuous basis with the NIH, particularly the labs of Jose and Lucy, and Fabrizio Magnelli, who was a colleague of mine for a little bit back in the day in Italy, and now we found each other again. So thank to all these people. And these are the resources that you can use to get more information. So as I mentioned, this is the source code repository. So if you're interested in Android development, this is the main place to go. But also some documentation is there, some examples. Particularly, you can find about a simple web page where you have links to the reference manual and to example files. The example files, there's one repository here separate because there's now, I don't want to tie the code too much to a complete input text. After all, NumD doesn't get distributed together with the tutorials. They're distributed separately. And these are examples that are basically going to give you this very general overview that I just showed you with the code. There's more specific tutorials for specific subjects. I think all of today's tutorials, and to some extent the ones from tomorrow and Friday, use the Converse code to some extent. So getting familiar with what it does can be useful to understand these tutorials better, but also to adapt them and derive your own methods. There's one 2D metadynamics tutorial, which is actually, I realized Jale has written it from, it's actually pretty much the mirror of the Blumen metadynamics tutorial, so you can actually get the same stuff. And this is it for the slides. And how much time do we have, Joao?
So we should finish this session in 2 minutes.
Okay.
But you still have 20 minutes if you want to do the demonstration.
Let me just cut it shorter than 10 minutes, like 5 or 10.
Okay.
So I have
I'm saying 20 minutes including questions.
okay. Well, let me take questions first then. I think that's more important than going through the demo. Yeah.
So I'm aware that for certain free energy calculations like ABF and the like, you are not supported on GPU accelerated AMP. But just for calculating a Colbert's...
No, you can. The ABF itself is not calculated by the GPU, but
Right.
you can use GPU with NumPy, that's fine. It's FEP, this is not compatible with GPUs.
Okay. So, but we can just calculate any of, you were showing the benchmarks earlier, we could, you should have no problems calculating like trajectories, the collective variables, and the accelerated version. Correct?
Yes. So the geometrical stuff that I talked about cannot work on a GPU. It just doesn't use it. Because GPU is done for the very repetitive, time-consuming work, and just basically calculating the van der Waals and Coulomb of water molecules and stuff like that.
Right.
That stuff is not part of the collective variables. The collective variables part is instead very bad for GPUs because it's not repetitive, because it just takes a handful of atoms that are special, and you define the collective variable on that. So a GPU implementation of that, for some special cases, could be good, but in general, is not really useful. There would be much more work that would industry speed up. So the CPU part on AMD, Colors is part of that, runs just fine for if some other part of the Hamiltonian is done on the GPU.
I have a question about the converge, because several times I heard this word. So is there any something like criteria to determine if my simulation is converged, or well converged, or no?
To know the truth, you have to know the result in advance. Then why are you doing a calculate in the first place? Practical approaches are you can take block averaging for running two independent simulations. Always keep in mind that if you have two independent simulations, they come from the same starting point. They're not really independent. So they're still correlated to some extent. So keep that in mind if you're looking for differences between the two. One thing that is important is that these methods, umbrella sampling, but WAM more specifically, or the bootstrapping method that come with the umbrella sampling, they will give us some error bars. Those error bars basically are the statistical sampling in the framework of the simulation. But it doesn't tell you anything about the landscape that you've not seen. If you're like stuck in a local minimum, you're unaware of what's around it. So be mindful that the error bars come from information that may be just from a local minimum that doesn't know what's around it. So the best way, really, the practical approach, since you're using a simulation to get the result and you don't know in advance, is try to use multiple simulations to get the result that you need. Definitely, I would say that being aware of what the method gives you is also important. Being aware of whether they have like an non-equilibrium regime and then an equilibrium regime. So yeah, ADF starts at non-equilibrium and then tests towards equilibrium. Metadynamics, not quite, but you can say toward the end, what you're adding is just one Gaussian at a time, no more than that. So again, you can average it out. I think the most important thing is looking at the trajectory of the simulation and seeing where the corrective variables go. Make sure that they behave the way they're supposed to do it. And one thing that probably is very useful is pinpoint the point where the metadynamics of the F looks like it has covered everything. From that point on, look at the histogram of the corrective variable. It should be flat. If it's not, then yeah, there's an answer.
I have a question. You mentioned parallelizing race iterations.
Mm-hmm.
The way you do that in practice is to get the contributions to RG of several different components and have those things be a collective variable, and then another one that is the square root of the sum of the squares.
Correct. Exactly. You may not be able to use a BF with it because when you go through the Latin library, who knows what function you're using. So ABF, the thermodynamic integration part of ABF, does not know that actually you're using the square root and there is an analytical derivative for it. Theoretically, you could also provide the inverse gradients through the constant function that's currently not implemented, but it could be. But yeah, this is one way of doing it. In general, parallelizing over threads, well, as I mentioned in the slide, I didn't say it out loud, you always should break up work so that each thread has their own work and each thread has their own memory. By making different variables, you're sure that each thread is going to have their own data to work on. And then you combine them together. Now, the combination is going to be done on one thread, but that's going to be very cheap. And yeah, as I said, I'm looking to ways to do this automatically because some of the variables we can actually do this. We don't even have, right now you would need to define different partial sums for the sum of squares of radius of iteration, and then take the square root. This could actually be done automatically. It's just that we need functions that will, instead of allocating one single piece, when you have radius of iteration, we'll allocate multiple pieces according to the number of threads. But that takes a little work, but it could be done in the future. But yeah, like in using the input file the way you should, you can already get the same speed up. You just put all the variables in different pieces, and these pieces are going to be computed in parallel.